In August of 2012, Voyager 1 crossed the single most significant boundary of its entire mission, the true edge of our solar system, and the moment it happened, its instruments recorded something that immediately confused the scientists watching the data come in. Every model built to describe that crossing predicted one specific defining signature, a clear, measurable change in the direction of the magnetic field surrounding the spacecraft as it passed from the sun's magnetic influence into the entirely separate magnetic environment of interstellar space. That change never happened. The field just kept pointing in essentially the same direction, before, during, and after the crossing, a result so unexpected that it left mission scientists with a genuine unresolved puzzle sitting at the heart of one of the most historic moments in the history of space exploration. For 12 years, that puzzle remained essentially unsolved. And in 2024, scientists finally published research that may have actually cracked it. This is the real story of that 12-year mystery, using nothing but the actual published research from the scientists who spent over a decade working to understand it. Every date, quote, and finding in this video traces back to genuine, peer-reviewed science and public statements from the researchers directly involved. Not speculation, not exaggeration, just an honest account of how long it can actually take to properly explain something a spacecraft already showed us. And back when most of the people now studying it were still working through the earliest years of their careers. Let's start with why this mystery mattered so much in the first place, because it wasn't a minor technical footnote. It struck at the heart of how scientists actually confirmed Voyager 1 had crossed the heliopause at all. The heliopause is the true boundary of our solar system, the point where the constant outward pressure of the solar wind, the stream of charged particles flowing endlessly outward from the sun, finally loses its battle against the pressure of the interstellar medium pressing back in from outside. Inside that boundary, the sun's own magnetic field dominates everything, stretched outward across billions of miles by the constant flow of the solar wind. Outside it, an entirely separate magnetic field, shaped by the wider galaxy rather than our own star, should theoretically take over completely, generated by forces and structures entirely disconnected from anything happening at the center of our own solar system, because those two magnetic environments come from completely different sources. Scientists expected the field's actual direction to shift noticeably the moment a spacecraft crossed from one into the other. In much the same way you'd expect a compass needle to swing if you carried it from one strong magnet's influence into an entirely separate one, positioned at some meaningfully different angle. That expectation wasn't just an educated guess either. It was built into decades of prior heliophysics modeling, going back to well before Voyager 1 even launched in 1977, when scientists first began seriously theorizing about what the boundary of the solar system might actually look like, and what physical signatures might mark a spacecraft's genuine passage through it. Early models generally pictured the heliopause as a relatively simple, well-defined surface, not unlike the outer skin of a bubble, with the sun's magnetic influence dominating everything inside that skin and giving way cleanly to an entirely separate magnetic environment immediately outside it. Under that kind of simple picture, a magnetic field direction, change wasn't just expected. It was treated, for decades, as one of the single most reliable, unambiguous signatures scientists could actually use to confirm a genuine crossing had occurred, arguably more definitive than any other single measurement a spacecraft's instruments might record. When Voyager 1 actually made that crossing in August of 2012, its magnetometer recorded exactly the kind of change scientists did expect in some of the data, a sharp jump in the density of charged particles surrounding the spacecraft, and a corresponding shift in energetic particle counts that matched theoretical predictions closely enough to eventually convince the mission team the crossing had genuinely occurred. Matthew Hill, a space physicist working on Voyager's low-energy charged particle instrument, Ives later described the moment his own team's readings shifted so dramatically that solar particles had essentially all vanished from their data, replaced almost entirely by galactic particles streaming in from beyond the solar system. A transition so stark that he recalled saying openly, at the time, that if the decision rested solely on his own instrument's readings, the team would already be confident the heliopause had been crossed. But the magnetic field direction itself simply refused to cooperate. It stayed essentially unchanged, pointing in nearly the same direction it had before the crossing, an outcome so far outside expectations that, as one of the researchers who eventually helped solve this puzzle put it, most space scientists had actually abandoned the assumption that a magnetic field shift needed to accompany the crossing at all, adjusting their working models instead, simply because the data refused to show what everyone had originally predicted. That's a remarkable admission if you actually sit with it. Rather than the data ultimately confirming the model, scientists were forced to revise the model to fit data that didn't behave the way anyone expected. This kind of moment doesn't happen often in a field as mature as heliophysics, where decades of prior observation and theory usually give researchers a fairly reliable sense of what to expect before a spacecraft ever reaches a given location. And for the next several years, that revision remained more of a necessary workaround than a genuine, satisfying explanation. Scientists could say with confidence that Voyager 1 had crossed into interstellar space, using other lines of evidence, particularly the sharp jump in particle density, to support that conclusion, but the specific question of why the magnetic field itself showed no meaningful change during the crossing remained a real, acknowledged gap in the underlying physics, an open question that simply sat there, unresolved, through the rest of the 2010s, occasionally revisited in follow-up papers but never definitively explained. That confirming plasma data came from a genuinely fortunate cosmic coincidence. In March of 2012, months before Voyager 1's actual crossing, the Sun produced a massive coronal mass ejection, an enormous eruption of charged particles and magnetic field that rippled outward through the solar system over the following year. When that eruption's shockwave finally reached Voyager 1's location in April of 2013, it disturbed the surrounding plasma enough to trigger detectable oscillations, and by analyzing the frequency of those oscillations, scientists were able to calculate the plasma's actual density with real precision, confirming it matched almost exactly what theoretical models predicted interstellar plasma density should look like. Don Gurnett, the University of Iowa scientist who led that specific analysis, described the moment his team recognized what they were looking at in genuinely emotional terms, recalling that the team literally jumped out of their seats upon seeing those oscillations, because the data showed unmistakably that the spacecraft had entered an entirely new physical region, one that matched everything theory predicted about true interstellar space, and nothing at all, like the environment still found within the solar bubble. That single piece of confirming evidence, born from a distant solar eruption that happened to arrive at exactly the right moment, became the final piece needed to announce the crossing with genuine scientific confidence, even as the magnetic field mystery sitting alongside it remained completely unresolved for another 11 years. Even though the mission team went public with the news in September of 2013, more than a year after the crossing itself, they were careful to frame the magnetic field puzzle honestly rather than glossing over it, acknowledging directly that this specific piece of the data simply didn't behave the way the community's existing models had predicted it would. Stimatios Krimigas, a principal investigator on Voyager's low-energy charged particle instrument at the Johns Hopkins Applied Physics Laboratory, offered one of the more memorable descriptions of what the crossing actually represented physically, comparing it to Voyager leaving behind the hot million-degree atmosphere of the Sun and entering a region dominated instead by the comparatively cold, roughly 5,000-degree atmosphere of the wider galaxy. It's a vivid way of capturing the genuine scale of the transition Voyager 1 had just made, even as the specific magnetic field puzzle sitting inside that transition remained stubbornly unresolved. The delay between the actual crossing and NASA's public confirmation wasn't due to any reluctance to share the news. It reflected how much careful, painstaking analysis was actually required before scientists felt confident enough in the overall body of evidence. The particle density jump, the energetic particle measurements, and eventually the plasma oscillation data captured through a fortunate solar eruption in early 2013 to announce the crossing with real scientific confidence, even while the magnetic field question itself remained conspicuously, honestly unanswered. The mystery only deepened in November of 2018, when Voyager 2 made its own independent crossing of the heliopause at a completely different location along the boundary, roughly 150 astronomical units from where its twin had crossed 6 years earlier. If the strange, unchanged magnetic field direction Voyager 1 had recorded back in 2012 was somehow a fluke, a strange local anomaly specific to wherever Voyager 1 happened to cross, Voyager 2's crossing offered a genuine independent chance to find out, using a spacecraft carrying nearly identical instrumentation built by the same engineers, launched only 16 days apart from its twin. It didn't turn out that way. Voyager 2's magnetometer recorded essentially the same result, a magnetic field that remained closely aligned in direction across the boundary, rather than the clean, expected shift scientists had originally predicted. Two independent spacecraft, crossing the same boundary 6 years apart, at two different locations, separated by a considerable physical distance, had now both recorded the exact same unexpected result. This wasn't a fluke. It was a genuine, consistent physical property of the heliopause itself, and it demanded a real explanation rather than simply being written off as an unusual coincidence tied to one particular spacecraft's specific crossing point. For years afterward, researchers worked through several competing hypotheses, trying to explain the unchanged field, none of them fully satisfying on their own, testing each one against the accumulating data from both spacecraft as the years went by. The breakthrough that finally moved this mystery from an open question towards something closer to a genuine explanation came in early 2024, In research led by scientists, including Alan Cummings, building on years of accumulated data from both Voyager spacecraft, along with careful theoretical modeling of exactly how magnetic fields from two different sources might realistically be expected to interact at a boundary like this. Rather than treating the heliopause as a thin, simple boundary line, the kind of clean, sharp division most earlier models had assumed, this newer research proposed something considerably more nuanced. The actual transition between the heliosphere and interstellar space, the researchers argued, isn't a line at all. It's a thick, genuinely complex boundary layer, a region where the magnetic fields from the heliosphere and interstellar space don't simply meet and separate, but actually interact, blend, and interweave with each other across a meaningfully wide physical zone, rather than switching cleanly from one to the other at a single, precise point in space. Cummings described the significance of this new framework plainly, explaining that it offers a genuine mechanism to explain the specific mystery of why the magnetic field's direction didn't change at either Voyager's respective crossing, something earlier models simply hadn't been able to account for. The physical mechanism proposed to explain this thick boundary involves a process called magnetic reconnection, something scientists have observed and studied extensively in other contexts, including in Earth's own magnetosphere and in the Sun's outer atmosphere. When magnetic field lines from two different sources, in this case the heliosphere and the wider interstellar medium, come into close contact under the right conditions, they can effectively break apart and reconnect with each other, rearranging themselves in ways that release energy and, crucially, can produce a considerably smoother, more gradual transition in overall field direction than a simply sharp boundary between two separate systems would otherwise create. Applied to the heliopause specifically, this process could explain why Voyager's instruments recorded such a smooth, largely unchanged magnetic field direction across what researchers had originally assumed would be an abrupt, clearly defined crossing. Under this revised understanding, both Voyager spacecraft may not have actually reached the true, pristine interstellar medium the moment they crossed what scientists had originally labeled the heliopause back in 2012 and 2018. Instead, they may have simply entered this newly proposed, thick transitional layer, a zone still meaningfully influenced by the interweaving of both magnetic environments, explaining why the field's direction appeared so continuous, rather than shifting sharply the way a cleaner, simpler boundary model would have predicted. Genuine, unambiguous entry into fully pristine interstellar space, according to this framework, would require crossing yet another boundary, one that may lie somewhat farther out than either spacecraft has necessarily reached even now. Merav Ofer, a space physicist at Boston University who has spent years studying this exact question, has been candid about just how much this new understanding has reshaped the overall picture of what the heliosphere's edge actually looks like. Rather than a simple, sudden transition, a bleep, as she's described it, marking a clean crossing from one environment straight into another, the heliopause turns out to be considerably thicker and more physically complex than anyone originally expected. A genuine boundary zone rather than a simple dividing line. She's also noted that this same body of research revealed the wider interstellar medium surrounding our solar system to be far less quiet and uniform than earlier models assumed, describing it as agitated and actively influenced by the sun's presence rather than the calm, largely unchanging environment many scientists had originally pictured existing just beyond our solar system's boundary. Ofer has gone further still, describing the interstellar medium as measured directly by the Voyager probes as genuinely different from anything researchers expected going in, admitting openly that scientists still don't fully understand everything that's actually happening in that region, even with well over a decade of direct, in situ data from two independent spacecraft now in hand. That admission matters, because it reflects something important about how this entire 12-year story actually unfolded. This wasn't a single research team working in isolation toward one clean answer. It involved multiple groups of scientists at institutions including Caltech, Boston University, and the Johns Hopkins Applied Physics Laboratory, each analyzing overlapping pieces of the same data set from slightly different angles, gradually building a more complete picture through years of published papers, conference presentations, and genuine scientific disagreement before converging on the thick boundary layer explanation that finally offered a coherent, physically grounded account of what both spacecraft had actually recorded. There's a genuinely important reason this specific mystery and its eventual resolution matters beyond simple scientific curiosity. The heliosphere functions as a real physical shield, deflecting a significant majority of the dangerous, high-energy galactic cosmic radiation that would otherwise reach the inner solar system, including Earth itself. Estimates drawn from Voyager's own data suggest the heliosphere blocks more than 70% of that incoming radiation, a genuinely enormous, life-preserving effect that every living thing on this planet has quietly benefited from for the entire history of life on Earth. Understanding the true, detailed structure of that shield, rather than relying on an oversimplified model of a thin, clean boundary, matters directly for predicting how consistently and how reliably the protection actually holds up. Information that carries real practical weight for any future planning around long-duration human spaceflight beyond our solar system's protective bubble. A thick, complex, interwoven boundary layer behaves differently in terms of how it filters and modulates incoming radiation than a simple, sharp dividing line would. And getting that physical picture right isn't merely an academic exercise, since engineers designing shielding for any future deep space mission need an accurate model of exactly what environment that mission would actually be flying into. It's worth being honest about exactly where this research actually stands today, because good science rarely wraps up with a single, tidy, fully closed conclusion. The 2024 research offering this thick boundary layer explanation represents a genuinely significant, well-supported step forward, but researchers studying the heliopause continue actively refining and testing this model against ongoing data from both Voyager spacecraft, for as long as their remaining instruments continue functioning, a window that's steadily narrowing as both spacecraft lose electrical power and shed instruments year by year. Scientists have also pointed to future missions, including a proposed dedicated interstellar probe mission still in the planning stages, as potentially offering the next major opportunity to properly test and refine this understanding. Since a purpose-built spacecraft carrying modern instruments specifically designed for this exact kind of measurement could offer a level of detail and precision. The aging Voyager spacecraft, remarkable as their contributions have already been, simply can't match at this point in their operational lives. Such a mission, if eventually funded and launched, likely wouldn't reach the heliopause itself for several decades, meaning whatever gap exists between the end of Voyager's active data collection and the arrival of a genuinely new interstellar mission could stretch on for a considerable length of time, leaving this particular piece of the solar system's structure only partially understood in the meantime. So here's what I actually want you to take away from all of this. For 12 years, one of the defining moments in the entire history of space exploration, Voyager 1's crossing into interstellar space carried inside it a genuine, unresolved scientific mystery, a magnetic field that stubbornly refused to behave the way every prediction said it should. Scientists didn't simply ignore that inconsistency or paper over it with a convenient assumption. They lived with the open question for over a decade, gathered additional confirming data from a second independent spacecraft crossing, and eventually built an entirely new, more sophisticated model of what the true edge of our solar system actually looks like, one considerably stranger and considerably more interesting than the simple, clean boundary line most of us probably still picture when we think about where our solar system technically ends. There's something worth appreciating in the sheer patience this entire process required. 12 years is a genuinely long time to sit with an open, unresolved question in any field, let alone one tied to a single, irreplaceable, non-repeatable event, a spacecraft crossing a boundary it can never cross again. Nobody could simply run the experiment a second time under slightly different conditions to gather more data on demand. Researchers had to wait, quite literally, for Voyager 2 to make its own independent crossing 6 years later, and then spend still more years afterward carefully building and testing a new theoretical framework capable of actually explaining what both spacecraft had already shown them. That's a fundamentally different pace of discovery than the kind of quick, dramatic reveal that tends to dominate headlines, but it's a far more honest picture of how real, careful science actually tends to work, especially when the data in question comes from somewhere no human being, and very few instruments will ever have the chance to visit again. If you want to know what future missions like the proposed interstellar probe eventually confirm about this thick, complex boundary layer, subscribe and turn on notifications, because this remains one of the most active, ongoing areas of research in modern heliophysics. Researchers involved in this work have already begun discussing what such a mission might need to carry in order to properly resolve remaining questions about the boundary's exact thickness and internal structure, conversations that are shaping the earliest planning stages of what could eventually become humanity's first purpose-built interstellar exploration mission. And drop a comment telling me whether you think Voyager 1 and Voyager 2 have actually reached true, pristine interstellar space yet, or whether you think they're still drifting through this newly discovered transitional zone. Because based on what scientists have found so far, I don't think that question is fully settled yet either.